Okay, so 3.24, there is a section back in 3.6.1 that I sort of skipped over, and the reason why I skipped over is because it sort of introduced an element that came out of nowhere, and I feel like it's more effective to introduce this concept via problem 3.24 than to sort of just introduce it in isolation and say, hey, here's this random little equation, just memorize it, right? So 3.24 wants us to prove that if an operator is Hermitian, then it has to equal the corresponding transpose conjugate, which means that element row m column n of this matrix has to equal the complex conjugate of row n column m instead of the conjugate transpose, right? So the sort of equation that Griffiths introduces in 3.6.1 is this idea that you can isolate QMN, right, row m column n of this matrix by taking it in the middle of an inner product of the corresponding basis vectors. Like this. And what he's saying is that, okay, if you want row m column n of this matrix, what you can do is you can squish it in the middle of an inner product between the em vector, em basis vector, and the en basis vector. And what this is going to do is it's going to give you that individual element of that matrix. And there's not really necessarily a proof. So the reason why I didn't go over this at the very beginning when we encountered it in 3.6.1 is because there's not really a proof. This is just sort of taking advantage of the way that matrix multiplication works. It's not necessarily a property. We're not introducing any new proofs or identities or anything. It's just you sort of have to understand how matrix multiplication works and take advantage of the fact that basis vectors are mostly zero except for a single element. So I figured I would go over it in a little bit more detail here so that we'd actually be able to just like look at it in the context of the way it is used. So let's suppose, right, that I have some 3x3 matrix, A, B, C, D, E, F, G, H, I. And let's say that I want to isolate F, this element right here, right? So how do I get this matrix and turn it into F? Well, immediately, right, sort of the thing I can think of is, okay, number one, if I'm only caring about this element F, I don't care about the rest of this garbage over here. So somehow, right, is there a way for me to turn this, number one, into a vector, CFI? And then from there, can I turn this somehow into just purely F, right? Well, so this is row 3 column, or sorry, this is row 2 column 3. I think I was getting my rows and columns backwards when I was talking about this, so apologies for that, just switch it over. But this is row 2 column 3, right? So supposedly, according to this expression, what this means is that I can get F by, let's write this in purple, actually. What they're claiming, or what Griffiths is claiming with this property, is that I can say, okay, row 2 column 3 of my matrix Q, let's say this is equal to Q, right, is going to equal taking the Q matrix and sandwiching it in between the product of the second basis vector and the third basis vector, like this, right? So let's look at this step by step to see what exactly this is doing. Well, what is this doing? If I'm multiplying Q, F, H, I, J, A, B, C, D, E, F, oh, whoops, I forgot my alphabet. I, like that. If I'm taking this and I'm multiplying it by basis vector 3, which is a 0, 0, 1, right? Well, if this is a 3x3 and this is a 3x1, what that means is that my resulting matrix is going to be a 3x1. In this case, if we just follow the standard matrix multiplication rules, this is going to be, right, A times 0 plus B times 0 plus C times 1. So C, and then over here, D times 0, E times 0, F times 1. So C, F, and then G times 0, H times 0, I times 1, I. So by multiplying it by basis 3, what I've done is I've just isolated out the third column on its own, and I discarded everything else, right? So from this point, Well, if I want f, right, because remember my original intention is to find f, if you then just take a dot product between E2 and this new vector, right, E2 dot product with CFI, well, E2 is just going to be, whoops, sorry, my timer. E2 is just going to be 0, 1, 0, like this, right? So if you take the dot product of this is 0 times C plus 1 times F plus 0 times I, which is just F on its own. So that's sort of, we're proving it, not necessarily mathematically, but by showing just that, this is how it results, right? You can isolate individual elements by multiplying your corresponding matrix with the basis vectors in certain ways. So if this is generally true, then how do I show that, this is necessarily equal to Q star and M? So let's do that. Let's write this out first. So Q and M is going to be equal, per this identity that we've shown, to be the inner product of En with Q hat multiplied onto Em, or Q hat acting on Em, right? Correspondingly, QMN is going to be equal to the inner product of Em and Q hat acting on En. And immediately, we know that Q is going to be a Hermitian matrix. So if Q is a Hermitian matrix, this means that this is correspondingly also equal to Q hat star En, Em, right? Similarly, if this is true, well, we also know that in general, right, you can switch the order of inner product by just taking the complex conjugate. So we also know that Q star and M is going to equal Q Em, inner product with En, right? So in that case, right, if my matrix is Hermitian, which is literally the whole definition for operators that can be represented, right? All in physics, or in quantum mechanics at least, every single operator is always going to be Hermitian, or represented by a Hermitian matrix. What that means is that this is basically the same thing as saying Q hat En Em, which furthermore is equal to that, right? So because of that, I've proven that Q and M is equal to Q and M star. By the fact that, I'm working with quantum mechanics, any sort of matrix I'm going to be dealing with is always going to be by definition Hermitian, and if a matrix is Hermitian, that means that you can take this and move it over to Q hat star. When you take the Hermitian transpose or conjugate of the matrix by moving it over to the other side of the inner product, the Hermitian transpose of Q hat is going to be exactly equal to the original matrix. And in fact, this isn't necessarily correct. I should rewrite it as the transpose with dagger, right? So in that case, we've effectively proven this problem and we're done with it.